All right, gentlemen. We are tonight, we're in Module 1, Section 2, Service Calculations is what we're going to be looking at. We're going to go over 2.00, 2.1. Actually only going to cover 3 pages tonight, believe it or not. But I think it'll be informative enough to for you understand the calculations. Calculations is where we're at. We'll be looking at a lot in the code book. You got your code book? Anything worthy of work telling about? Anything happen at work? Not for you? Are you working at all?
I'm on call right now.
Are you?
Yeah. So
Still kind of in the service department?
Service department, and then if they need me, I got Thursdays free, but they haven't called me in on them.
They called you in.
Or nights or weekends, whatever they want.
Okay. Where are you working at, James?
Michelin, off right on the backside of Donaldson Center.
Y'all doing demo right now?
Yeah,
right?
yeah, we're doing all demo.
Not working on anything hot, are you?
No.
Remember, you're on tape.
Yeah. No, we don't,
I'm just
They
kidding.
put a light detector in.
we always, we go up there with a ticker and then have Kelton kill the breaker.
Kill the breaker.
And then sometimes we have to kill more than just that one.
Sure.
Mhm.
Y'all just demoing right now.
Yeah.
Warehouse kind of thing?
It's like a.
Office warehouse?
Yeah, it's almost like an office building. It ain't got, but I think it's got 4 office rooms right now, and then like one like big conference room, and then a little small bathrooms.
Okay. Older building? Ain't it an older building?
Yes.
How old is it?
I think it was built.
Like the 70s or something.
I think they said it was in the 70s.
So it's you and
Me, Kelton, and my helper Jose.
Jose. Yeah, all right, we're good. So you're doing service calls when you do? You call?
Stuff. A lot of like restaurants, like Cheesecake Factory, will have the way they wash their floors is or like behind the stove, they'll take a 5-gallon bucket,
Mhm.
just chunk it back there, and it tends to fry switches and outlets and that kind of stuff. So
I gotcha.
get a lot of that, and then other odds and ends.
Well, like I said, we're gonna do service calculations, guys, on page 14. We're gonna turn there. The biggest thing, we got some objectives that we wanna do. There's 3 objectives. Make the service calculation for, of course, it's residential, but that's okay. For residential, so there's 3 things there. 1, calculate the minimum service size for simple electrical installation. So we're going to get through that, which y'all have done that in the other class. Should be familiar with you. B, make service calculation for a single family dwelling, which is the type of house that most of us live in. And C is make a service calculation for multifamily. Now what is multifamily? Apartments. Yeah. And of course, because of apartments, there's different rules that apply. But we'll be looking in the code book, a lot of it in the 200s, 220 kind of areas where we'll be going. As you can see there on page 14, there's a lot of information as far as looking in the code book that we'll be going to. The biggest trade term that we want to kind of break this down, just kind of look at it, called service equipment. And we kind of see what all is involved in service equipment. The necessary equipment usually consisting of, and so we have, it says a circuit breaker or switch and fuses and their accessories connected to the load end of the service conductors. And so, typically, we got, if we're dealing with residential, which is what we typically are right here, at least at what it tells us, and that doesn't work. We usually have what on the outside of the building?
Meter.
We're going to have a meter. All right, and that doesn't work well either. So we'll have our meter. Typically on a house, how many amps? 200 for the most part. Now here's the thing, if we're looking at this thing at our home, sideways, and that's our meter, for us to be able to not, and this is commercial or residential, it doesn't really matter. For us to be able to just put a meter on the outside and not have any type of main disconnect, that means on the outside, you must put the electrical panel directly behind the meter. In other words, you couldn't come out of this meter, go through, and even set this thing, 10 foot down the wall. Because what happens is this is unprotected wire. It makes sense. And so if it's not, and of course here, there's really no unprotected wire, is there? Not inside the building. Okay. Now what you could have done, if I'm not mistaken, this what would be classified, I think we looked at this last week, what you could have done actually would have been come underground and get, of course, then you'd have to have it, let's say residential, it would have to be an on-slab house to be able to do this. Because if it's in the crawl space, then I don't think you could. So you'd have to get underground, and then you could come up into a panel. Okay, because then they're not inside the building, right? But typically, if you're going to put a meter on the outside and you're going somewhere else in the house or the building, if you got your meter, let's say a 200 amp, then we're going to set, a 200 amp disconnect. And then if you do that, which I would kind of recommend to do anyway, and then our service risers always, if it's an overhead, it's going to come to a weatherhead like this. Who's responsible for building this? We are. Okay. But now if it comes underground, like let's say from a power pole over here that's got a transformer on it, and they're going to set up a service mast, they're going to come underground and come up into the meter. Who does that?
Duke or energy company.
Yeah, the power company does. Usually all we have to do is give them this piece of pipe down and turn it into the ground. And they do the rest. So, just depends overhead or underground. And again, this is our point of attachment here. And we usually just hang them out the wires and then they connect to it. Now one of the things you got to have, especially if you're overhead, you have to give them a service point of attachment. In other words, that's usually like a through bolt on the building or on a house, to where when they bring in their overhead riser, they can do what? Something for them to attach their wires to hold it off. That's a requirement that you have to do. Okay. So, and it just takes the tension off it takes the tension off your service riser by them being able to go over there and clamp to that. Because a lot of times this may come, I think the general rule is, I think they can come like up to 80 foot overhead without setting another pole. I think I'm right in saying that. So that's kind of what we're talking about here, service equipment, what we got going on, overhead and underground. I don't like that eraser. Okay, so let's look at our definition there. And it is the load side, right? Because the line side of that meter is what? It's power company, right? The load side is typically something we're bringing in, okay? And again, but down this meter, whether it's overhead or underground, it's something to think about too, because I think people do this wrong. Alright, so this meter, inside of it, you got, which is the load side and the line side?
Line side would be top.
Regardless, whether it's underground or overhead. Y'all agree? That's the line side regardless. I've seen people bring in underground wires and hook them right there. Seen it more often than not. Okay. And so, but this is their load side regardless, isn't it? And of course, in saying that, then what would have to be, if there is an underground conduit coming in, as far as installing this pipe, more than likely you wanna do what? You wanna put it off to the side, don't you? If you put it in the center, you gotta bring those wires in, but you also gotta bring your wires out, and it becomes a cluster right there. So some things to think about. Where are we gonna ground this service at? In the meter kin? Say yeah.
Yes.
Okay. Well, that's where a ground rod's gonna come to, isn't it?
Yeah.
You know, city of Greenville or Greenville County, how many ground rods are required? 2. How many feet apart do they have to be?
6 foot, I
I
think.
think it's 6 foot, minimum of 6 foot. They can be further, that's minimum 6 foot. Driving the ground rods, straight down, gotta be completely buried, correct? Can they be sticking up 6 inches? No. What if we ran it in the rock? What can we do? We got a couple options.
You can cut it.
Oh, we can cut it, yeah, that's a good answer. He didn't say that, that's a good answer. All
I
right.
was just playing.
Nah, and what we're gonna do, we're gonna make this wire one continuous piece, aren't we? That's one thing. The other 2 things we could do, we could put it in at a 45. And the other thing we can actually do, and we'd have to look it up, and we may do that in a minute, I'd be curious to know. Matter of fact, let's try to see if we can look it up. If we're gonna lay a ground rod horizontally in the ground because of rock, what's the minimum cover depth? Y'all find that for me in the code book. This would be called, let's let you know, to kind of help you out, this is a grounding electrode. A grounding electrode. So anything grounding, we know what section we're going to.
250.
250. We got narrowed down that much. Let's see if we can find what depth we would bury that horizontal electrode. And I'll look too. What's the minimum length a grounding electrode's got to be?
8 foot, ain't it?
8 foot?
Yeah, 8 foot.
Yep, that's 250, 52, 85, isn't it? Rod and pipe electrodes must be 8 foot in length. That means you can't cut it, James, unless you got one longer than 8 foot. So, not throwing you under the bus or nothing. Did anybody in here ever cut a ground rod?
I did, because it got stuck. And I had to put it somewhere else.
You never have? Really? I have to admit I have. But I was in West Virginia and I was permitted to. So,
I got
What was it, a 10-footer?
no, it's an 8 footer, but in West Virginia, it's all rock.
Oh.
I went to the local inspector, who was the hardware salesman in the town, and I told him my situation, and he also was the inspector, and he says, go ahead and cut it. Okay. So,
I've got 250.53
uh-huh.
G.
G, there you go. I just found it myself. Matter of fact, I got it highlighted. Must be how deep?
30.
30 inches, yeah, 30 inches deep. Be buried in a trench at least 30 inches deep. The upper end of the electrode shall be flush with the below ground level unless the above ground end electrode attachment are protected against physical damage. So, 45 degree is the other thing we see there, that where rock bottom of the counter electrode may be driven to an oblique angle not to exceed 45 degrees from a vertical or where rock bottom is encountered. So we got some options there with our grounding electrode going. connected, load into the service conductors to a building or other structure, otherwise designated area. And that's the thing too, you know, thinking about, you know, we want our service to be a designated area. We don't want multiple services on a building. We want one for the firemen, don't we? And so we usually have a designated area that's called the service entrance or service area. And, you know, particularly on a house or residential or commercial, we hope there's a electrical room, and that's where we're gonna come into. But the last thing we wanna do is spend a lot of money on service wires, because that's where we really get costly. And it says that it intended to constitute a main control and mean to cut off supply. So that's the purpose of like that disconnect outside or circuit breaker or whatever it happens to be. But again, you don't have to have that if you're directly, just like if you were, I mean, this is what happens with us a lot on commercial facilities right here. We see this more often than not. 2,000 amp service. So we have a transformer outside, don't we? We got a building, we got a switchboard. Okay. We got a switchboard inside, 2,000 amps. Where's the meter probably gonna be located?
On the transformer.
Yeah, on the transformer, isn't it? Okay. Means nothing we gotta do there. Let's say they decide to put the meter on the building, which sometimes happens, then what must we do?
Put it directly behind it.
We gotta take a 1-inch pipe out of here and get over to the transformer, don't we? But if that's not there, or either way, it doesn't matter. And then with our transformer, we're gonna have service wires, aren't we? Now notice we're underground. Okay? And so we stay underground and we come up inside the building and there's no main needed there, is there? Okay. Well, that'd be a very costly main outside. We had to do that. So underground, you put in a bit underneath, you got cover, you got at least 2 inches of concrete cover, and you're safe to do what we're trying to do without a main outside. Okay. And really, you're just designating that as the cutoff point to the firemen when they come in. Now, one thing's required, since there's no cutoff outside, the local fire marshal probably require the building person to put a commercial facility to put something called a Knox box on the outside, which is the key. Get into the building, because they got no, I mean, they can cut the power off here, of course, and that's probably where they're gonna throw it in this situation, aren't they? So, but that's what that is, that's a designated area, that's usually within a room, called the electrical room, isn't it? And that's usually, we want to minimize this length from here to here. Generally speaking, the transformer has to be a minimum of 10 foot from the building edge, generally speaking. One of the other things, as far as the transformer, when we're putting it in outside, understand that there's windows, we're looking down on top of this transformer, there's windows we gotta hit in, primary and secondary. You better make sure you know which one's the primary and secondary. I think primary is on this side, and secondary is on that side, if I remember right. And it'll be the same. And so again, we make sure that when we turn these pipes up, we're getting inside of the secondary side with our conduits. And usually what we have to do with this primary side, we got to stub them out of pipe. Usually 1 or 2, depending on the service size. Typically no more than 2, but these are usually what size pipes?
4 to 6 inch ones.
Yeah, 6 inches for the most part, James. 6 inches. And they really prefer to have a long sweep L because they really want to do it the easy way. But that's on the primary side, usually 1, sometimes 2, and all we do is just stub it outside the pad and that's it. They pick it up from there. So, the biggest thing is understanding, and you usually from the project manager, if you're in the field, you're getting a layout. Matter of fact, I usually give them a layout, a printed copy from Duke Energy, because it gives you usually the requirements for the pad and the size, and whether it's got to be if it's a small pit or a flat pad. There's 2 types of pad. There's a flat pad and there's a pit pad. Most of the time, the larger services require a pit pad, a large pit pad. And again, those are just recommendations from Duke Energy, and we usually get the general contractor to build the pad. We don't want, because we're not concrete people, right? We don't want to build pads. You ever built one?
Built a bunch of them at the airport.
Oh, did you? Y'all did your own pads?
Yeah, we did our own pads.
Did you? Rebar in them?
Mm,
How long do you think it took you to build a pad?
Yeah.
Just a guess. No, not just, what do you, how long?
The
you
building the form and everything, it took about 2 hours.
Oh, that all?
Yeah. Well, like, once you got the hang of it, now, like, the first one, it probably took about 4 or 5 hours on the
Okay.
first one. But then once you got the hang of it, then it was,
Okay. Y'all
And
poured the
then- and then-
concrete and all?
yeah,
Finished them?
yeah.
Did you?
Most of the time, it was, me and Ricky,
Really?
yeah, Walt's helper Ricky.
Yeah.
Yeah, me and him did all that finishing out there for the
Really?
underground and everything.
Cool. Okay. All right. Got some services, that's kind of what we're talking about tonight. We're gonna get into some calculations. Look, on page 14, actually a 9-step process, and it's what we're gonna look at first. 9-step. Let's turn to NEC 22012. Let's see what we got there. So 22012, so step one, I'm gonna kind of put this on the board as we go. Step one, we're just talking about lighting load. So step one, let's see if I can get a better marker. And how about that chart? See it there? You understand it? Let's say for residential, we're just gonna do a house, general lighting load by occupancy. And as far as reading that table, dwelling units, how many volt amps per square foot does dwelling take up?
Just 3.
3. So, we got a 1,500 square foot house. It's 3 VA. What's VA? Volt amps. What is volt amps?
Once.
Watts. Okay. So you'd be 1,500 and it'd just be 4,500. That's step one. That's what it's trying to tell us to do here. If you read here, compute the floor area of the building using the outside dimensions of the building. This area is listed to determine the general lighting load for a particular occupancy. So each one varies. Let's look at, for the gives one, let's look, what about a warehouse? Let's just say we had that was 4,500 VA for a house. House, 4,500 for just, but let's just say, for the sake of doing it, I know we wouldn't have one this small. Let's say if you had a warehouse that was 1,500 square foot. Let's just say, what's your lighting load? What is their multiplier?
Quarter.
Yeah, quarter, which is what, 0.25? So what's 1,500 times 0.25? Yeah, do the math.
$375.
A little bit of difference, isn't there? Now, this is not going to happen in reality because we don't have a 1,500 square foot warehouse. You know, but again, let's say we had, let's go back to last week where we was figuring lighting loads for James's house. And so it's 20,000 square feet times 3 is 60,000. We did the same thing with the warehouse. We did 20,000, that's a little bit more realistic there. 20,000 square foot warehouse. So then what is their load? Like 5,000? Is that what that is? So considerable difference because we're not going to light up a warehouse like we're going to light up our house, are we? Okay, and so that's step one. So that's the first thing you got to do there. And it gives some examples. And see there the multiplication factor per square foot. Now I will say this much: in doing residential, there are some rules which we'll get to later. I'm not sure we'll get to them tonight. But there's some areas in the house that don't count for square foot. if it's not livable, you know, it's not livable space. If it's not heated space, then it's not counted as square feet. But we're not gonna talk about that right now. We're just trying to, number one is lighting loads. Okay. Step number 2, multiply floor area determined by step 1, unit load and count, which is kind of what we're just doing. Compare its value to the total installed lighting used for general illumination and use the larger of the two. So it's step 2, you're actually multiplying the floor area determined by the load area and calculate the general. I'm not reading that again. Compare this value to the, so we're actually just looking at whatever was installed. And you compare the two. You know, if you had, let's go back to this warehouse. Let's say we had 20,000 square foot, okay, times 3, times 0.25. That's 5,000. All right, let's say in this warehouse you had a 6-foot T5 high base. So that's about 350 watts per light fixture. Okay, round it off. Let's say 350. Let's say in that 20,000 square foot building, in that warehouse, we had, let's just say there were 20 light fixtures. What is 350 times 20? That gives one every, yeah, that might would work, just for what we're trying to do for now.
7,000.
How much?
7,000.
7,000. So then by step number 2, which one are we going to use?
7,000.
We're going to have to use the 7,000. So we should use the larger of the two. So step number 2 is look at lighting and use the larger. Compare lighting. Use the larger. All right. Step number 3, calculate the lighting loads used for other than general illumination, such as for task lighting, exterior lighting, accent lighting. Refer to the applicable sections, and you can look there, 220.14D, we can look at that, 220.14D. Analysis applying a luminaire shall be calculated based on the maximum volt amps of the equipment and lamps. So you're just doing volt, actual load there. 220.14E just talks about heavy duty. Outlets for heavy duty lamp holders shall be calculated a minimum of 600 volt amps, 600. Okay, so that's something to remember. Matter of fact, if you look at F, it talks about sign. If you got a sign on the building, you got to calculate that different. It's a sign is 1,200 volt amps. Am I right in saying that? 1,200 volt amps for a sign. Commercial building, you're probably going to have that, aren't you? Okay. The other thing you have to consider is maybe if it's a store up front, you may have some show window lighting. If you look there at G, it says it's 200 volt amps per foot. So show window, 200 volt amps per foot. So we had a 30-foot building across. You know, you got to take the dimensions of the building, so 30 foot across. So 30 times 200 would be adding what, 6,000 volt amps to that load. And if it's got a sign, we're adding another 1,200, aren't we? So that's 7,200 volt amps right there up front in a store. Okay. So that's just some of the other things. Let's see. The track lighting, 220.43. It says for show window lighting, which we just talked about that, not less than 660 volt amps per linear meter or 200 volt amps per linear foot shall be included, which is what we were just saying. Okay. So, some other ways. So, number 3, we'll just put other lighting loads. Number 3. Number 4, what are we calculating?
Receptacle loads.
Receptacle loads. Refer to applicable, let's look at their sections. 22014A. And just talking about specific, for specific appliance, not covered 22014B, which shall be calculated in ampere rate. So we're just gonna go by the, in other words, we got something specific, something special, we're gonna find what that is. You know, just like, for example, to get the volt amps, let's say we got a 30 amp, 240 volt plug. How are we gonna get the volt amps? How are we gonna figure out a 30 amp, 240 volt plug? How are we gonna figure out how many volt amps it is?
30 times 240.
Yeah. And we don't need to do it, but it's like 7,200. Okay, that's how we get to that. That's just a specific thing. All right. We look at the other part, H, mixed multi-outlet assemblies. If you look at H there, in other words, you got a multi-outlet strip on the wall. If you look at the rule there, it says for every 5 foot, by the way, a general purpose duplex outlet is 180 volt amps, 180. You want to know that. And because of that, if you look at rule number 1 under strips there, for every 5 foot or fraction thereof, you got to count it as 1 outlet. So here's the thing. Multi-outlet strips usually come 6 foot long, typically. Let's just say it is anyway. So it's 6 foot. So how many volt amps is this multi-outlet strip? By reading that rule there. Where appliances are, well, let's say they're unlikely to be simultaneous. Let's say that the outlets are unlikely to be simultaneous. How many volt amps is this strip?
Should be 360.
360. Very good, James. Well, there's 180 for this. And because it's a foot over, not a major fraction, it just says fraction over. So it's 180 for that. You get a total of 360. If it would have been 8 foot long, what would our volt amps would have been?
Same thing.
Same thing. Yeah. Okay. Now that's if it's not, but look at number 2, where they would be used simultaneously, like maybe at a desk or something, possibly. Every foot, so every foot counts in. So this 8 foot one then becomes 180 times 8, doesn't it? Big difference. That's the key. Are they going to be used simultaneously or not? So there's 2 different rules there. That's receptacles. We look at receptacle outlets 22014I. In fact, there's the rule. That is covered 214J. Receptacle outlets shall be calculated not less than 180 volt amps for each single or each multiple receptacle on one yoke. In other words, that right there is how many outlets? 2. That's 360 volt amps. So, step number 4, receptacle loads, isn't it? All right. Step number 5, appliance. Apply applicable demand factors for specific applications referred to. So 22044, what's a demand load? Let's talk about a demand load. What is a demand load? Let's just talk. What do you think a demand load is? Is your house, let me ask you this way. Unless you have kids, okay. So if you have kids, you're exempt from this question. Do you turn on everything in your house? No. James, you have kids. Does everything on your house get turned on?
Yes.
Yes. Okay? Because they leave everything on. They leave every light on. they leave everything on at all times, and they don't think it's necessary for it to be cut off. Because then it would become a strain for them to come back by and actually have to cut it on. So therefore, they think if it stays on all the time, that they don't have to go through the effort of cutting it off and then back on. Am I right?
Yep.
So therefore, people with kids are exempt from that. But generally speaking, demand factor says, okay, in your house, you know, Nate, it's just you and your wife, you're probably gonna cut on 30% of your lights. Maybe. And you're probably pretty tight, so you probably got a candle you walk around with. You don't cut on any lights.
Sometimes lightning bugs, candles
Yeah,
get expensive.
that's right. So because of that, we have demand factors, saying people like Nate, and so we try to take a, you know, he's one extreme and you're another, and so we kind of got to get, you know, in between here. And so there's some demand factors. If you look at 22044, it talks about it. And then if you look at table 22042 up above there, lighting demand loads. See, like matter of fact, let's look at a warehouse. A warehouse says that for the first 12,500 what? 12,500 square foot? No. 12,500 what? Volt amps or watts. We're going to take it at how much percentage?
100%.
100. And then everything over 12,500 in a warehouse, we're going to do 50%. Okay. 50%. Big thing. 22044, demand factors for dwelling receptacles. There's a table there. So the first 10 kVA, okay? Now what's 10 kVA? Let's talk about this and make sure we understand this. 10 kVA is how many volt amps?
10,000.
10,000 volt amps. So for the first 10,000 volt amps, we're going to do 100%. And then everything over, we're going to do what? 50%. Big difference. So that's and we go over. Let's go over to. Let's look at these other articles right quick. Article 610 talks about. This would be a commercial installation here. The 610 is cranes and hoist. And there's a demand factor, 1614E, number of cranes or hoist. And again, if you're in, James, you did a crane installation over at, what's the name of that place? All Metals.
Oh, yeah.
Yeah. Do they typically don't run all the cranes at one time, do they?
No.
One at a time. And so because of that, there's factors here. Like 5 cranes, the demand factor is like 0.84. Y'all see that table there?
Which table again?
1614E.
Oh.
All right, while we're back, let's go to 620 and it talks about the elevators. Again, are all the elevators going to run at one time? More than likely not. And so there's 62014 is the demand factor for elevators. 630 is electric welders. Demand factor. Okay. Multiplier, duty cycle. Electric welders, we get into duty cycles and multipliers that we use for both of those. There's 2 tables in there. Talks about that. Article 660 is x-ray equipment. Again, probably in the doctor's office, there's probably going to be one x-ray equipment. X-ray equipment, I'm looking to see, where am I finding it? Minimum size insulation, capacitors, grounding, wiring terminals. I'm looking, y'all help me. Can we reduce it? somewhere. Minimum size conductors, wiring terminals. Am I missing that somewhere? I'm not seeing the demand factor for X-rays, are y'all? Disconnecting mains. Well, branch circuit, in past it was branch circuit overcurrent shall be not less than 50% of the momentary rate. That doesn't really. Feeder conductors, 100% of the momentary demand rating. I guess this would be where it's applicable. Of the two largest apparatus plus 20% of the momentary ratings of other X-rays. So 660.6B. Y'all agree? That would be, that's talking about demand factor there for X-ray equipment. Okay. And then lastly, 695, which is a fire pump. Very important. What's one thing we do with a fire pump? What's one of the things about a fire pump that you really need to know? Has its own service. Because the last thing we want the fire pump to do is what?
Cut off.
Cut off. But it has its own service. Usually maybe from the same transformer as your incoming power from the building, but definitely not on the same breaker, is it? Has its own meter, doesn't it? On power. And we're looking for demand here. Y'all help me find it here. Voltage drop. Junction boxes. Y'all find it, let me know. I'm looking. Overload. Feeders. Conductor size, it just talks about 125% of the fire pump plus 100% of the associated fire pump accessory equipment. That's the only thing I can see. I don't see as far as, well, there wouldn't be multiple, I don't think. So I think that's probably the only thing I'm seeing referred to any kind of demand factor, which is, where'd I find that? 695.6B. The only thing I see as far as any kind of demand factors for a fire pump. Okay. All right. So we do. So we got demand factors. So step 5 would be demand factors. We have to applicable to certain situations. I picked up the wrong marker. That's number 5. Number 6, calculate all the motor loads in accordance with 220.50. Let's turn back there. Your 20-foot motors shall be calculated in accordance with 430. So it gives us some rules there. The biggest thing about motors is listed down below there. Use the NEC 430-17 to determine the largest motor. And so we have some tables in 430. So why do we want to determine the largest motor is listed down below there? Because we do, generally speaking, motors are continuous duty unless they're listed differently. And so if we got more than one motor, we have to do 125% of what motor? The largest. Then how much of a percent of the rest? What does it say there? In your book. Step 6.
100%.
100%. Okay. 100% for the, and that's the key too, the largest motor. You may have two 7 horsepower, one 5 horsepower. Let's just say, I don't know, let's just throw a number out there. Let's say these are 20 amps, and let's say these are 15 amps. What's going to be our total amperage for these 3 motors? What we're going to do? We're going to take 125% of what?
1 7 horsepower.
1 7 horsepower. So we get 20 times 1.25 is how much?
25.
25?
Mm-hmm.
And then we're going to do what? We're going to add what to it?
20.
20. And then
15.
15. So it's just we wouldn't do this twice. Just one motor. Even though they're both the same size, one's 125%, one is not. Very important to remember that right there. You do it. So step number 6 is motor calculations. Motor calculations is found in the code book. What section? 430. Anytime you get a question, matter of fact, 430, so let's turn over to 430 right quick. 430, 148, I think is where we want to go. I mean, yeah, 430, 248. 430, 248. Well, 3248 is amperage for single-phase motors. 43250 is amperage for three-phase motors. That's 2 tables that you need to remember. 43248 is for single-phase. 43250 is for three-phase. Okay. You remember those 2, you got it booked. Okay. So that's step 5. Step 6. Step 7, what are we doing? What does it say? Somebody read step number 7.
Calculate both the heating and air conditioning loads and use only the largest of the 2 in the total load calculation.
Yeah. Largest. Why the largest of the 2? Why just the largest? Why not both?
Unless you got kids, you only run them one at a time.
Yeah. Unless you got kids, you only run one at a time. That's right. Okay. And you'd have to have a pretty sophisticated system to run both of them at the same time. And now there are a few little quirks about that we're not going to get into tonight. Like if you got supplemental heating, it's a little different. But for generally speaking, 99% of the time, most people's houses or something, it's the larger of the 2. And I will say this much, generally speaking, typically the largest load is heating, for the most part. Your power bill usually more in the summertime or wintertime? Winter? Yeah. Why? Because it's a larger load. Okay. And our houses probably aren't insulated very well either, like they should be. So, at least mine, I need better windows. Okay. I lose a lot of heat in my windows. Even though they're double pane, I know I need to buy new windows. They're high, man, they're high. Windows are high. Ooh. Okay. All right, step number 8, if you look here, add all the loads. Resilient load in the volt amps is divided by the system voltage, and that's one thing I want to talk about too. Here, just if it's a single, well, first of all, keyword system voltage. Make sure that you're using, like on a single phase, if it's 120, 240, your system voltage is what? What is your system voltage? 120, 240 single phase.
240.
Yeah, it's 240. What is your system voltage? 120, 208, three phase. 208 times what?
Square root of 3.
Square root of 3, which is what, 360? How about 277, 480, three-phase? How much? 480 times 1.732 equals what? Maybe 830, see if I'm right. Close enough.
31, yeah.
Yeah.
Close enough.
Okay. All right. The system voltage, that's what we're gonna do. So we've done all this. So number 8 is add all the loads. And I'm gonna put system voltage is important. All right. System voltage. All right, number 9, I think this is the last step, isn't it? Look at what number 9 says. At 100% of the non-continuous loads and 125% of the continuous loads. Okay. And a lot of that's going to vary. Let's go back and just kind of think about some of these things. Can lighting be continuous? Yeah. Where would lighting be continuous?
Commercial, anything pretty much.
Yeah, probably not in your house, but in a warehouse?
Definitely.
Yeah. At the grocery store?
Yes.
In a hospital? Other lighting loads, how about that sign? It's gonna stay on all day? At least 8 hours, isn't it? Okay. So we got other things. How about motors? Gonna run all the time? Yeah. Okay. Heating and air, is it gonna run sometimes more than 3 hours? I hope not, but it could. Sometimes in the heat of the winter, it runs all night, doesn't it? And you're going, Lord, please let it cut off. Okay. You go throw on another blanket and turn it down while your wife ain't looking. Right?
I have done that. Got it.
Of course, we like to sleep when it's cold. We
I
sleep better. I sleep better when it's cold.
I love
Yeah. Now, most women just the opposite, aren't they?
it. Got it covered up.
Yeah. So, step number 9, we're just gonna say 100% non-continuous, 125% continuous. And that takes us through what we're trying to do, through this whole section here. Okay. All right, let's go through a couple more things, and then we'll take a break. So we got this, you got that, everybody good with that? I'm gonna erase this. I think we're all good. Let's get through the next couple of sections here, and then we'll take a break. Maybe that gets that to about 7. Calculation for simple electrical installations. Total calculated load of an OXY is determined by adding all the individual loads after any demand factor. That's what we just did. Generally, the total calculated load for a particular OXY determines the minimum, and this keyword, determines the minimum size service it should have. So our calculated load is what's going to determine the service size, right? I mean, it kind of makes sense. The following section provides an example of how to make these calculations in a variety of situations. So let's look at a couple of examples. So we got a pump house. Anybody ever seen a roll pump house? I used to have one. Okay, my grandparents' house. They had a well, they had a pump, they had a little light, you know, and you had a little heater in there to keep it from freezing. So a little pump house. I mean, that's what they had. Okay, matter of fact, I was on. I wasn't even on city water till about 10 years ago. I had a pump. Now mine wasn't a pump house. It was actually just a pump, you know, in a concrete thing outside, and because the pump, now the pump is at the bottom of the well. And so there's no need for that. And like in the old days, the pump was actually, you know, there was a shallow pump, so the pump was up at the surface, and so you had to, you know, keep it from freezing up. Most of the time you just had to put a light bulb in there in the room, keep it from freezing. That's all we did. Enough heat would be generated from that light bulb to keep the pump from freezing. So, but that's kind of, so look here, we got an electric meter. So the floor plan for a small rural pump house is in figure 3. We look down and see there below. We got a single pole switch, throw 120 volt, 15 amp safety switch. Notice you got a meter with a service mask. So this switch, now look at the switch, must be marked, identified as being suitable for use of service equipment. So it has to be, when you buy this, it has to be something called SE rated. It has to be a sticker on there. It says it's SE rated. If it's not service equipment rated, because this, what is this disconnecting doing? It's a service entrance. It's a place where you go and you cut it off. So it has to have a sticker on there that says SE rated. When you buy it, you just can't have just a regular disconnect down. It's got to be an SE rated disconnect. And that's what that's saying there. Okay. And all we got in there is that. We got a pump, a disconnect, a light, and a switch. So, let's look at it. So it's a shallow well pump. Like I say, that's typically in the old days. And that was probably a 40 or 50 foot well. Matter of fact, what happens is there's 2 layers of water, and underneath the earth, or at least there's probably more than that, but I know there's 2. The first layer used to be these shallow wells, and they were, and that level can run dry. And so people got smart and started going down, like my well at my house was at the second tier. Well, that varies as far as that depth. That first one's usually 25 to 50 foot, but that other one really can vary. At my house, when I put my pump in, it was almost 500 foot deep. And of course, they charge you per foot when they dig in that, so it gets pretty costly. And if it gets so far down they don't hit, they have to dig another one. Guess what? You still paying for it. It can get really costly. So, but when my pump gave out, it was cheaper for me to get on city water then. But when I did my pump, there was no city water at my house. I didn't have a choice. So that's what this is here. This is just a pump, like at a house or something. 3rd horsepower, 115 volt single phase motor, 1 wall switch controlled lighting fixture with a 60 watt lamp. So it's a load and service size are calculated by using the following step. We're going to go to, we see that 220 does not list a small 22012, therefore we got to use 22014A. And so if you look there, we're going to go over, if you look at step 2, it says 436A requires that where the current rating of a motor is used to determine the ampacity of conductors, the value given in which that's those tables. So we need to go to 430, 248, don't we? And we're going to look up the rating of this motor. And somebody tell me the 115 volt 3rd horsepower motor, how many amps it would be.
Should be 7.2.
Yeah, 7.2. Now what are we going to do with that 7.2? Motor, well pump, what kind of load?
Continuous?
Continuous. So tell me how much that is. Yeah. 9 amps. We want to get the volt amps. What's our voltage? 115 or 120?
120.
Ah, very good. So 9 times 120 is how much? Like 1,080 volt amps? Is that right? Okay, so 1,080 volt amps. Now we got our 60 watt bulb we're going to put on there. And that's going to give us what? 1,140 volt amps. Okay. 1,140 volt amps. If you look there, that's what it says so far. So we've got 1,140 volt amps total. Then we're going to want to find out how many amps this is. And so we're going to divide this total now by what? Oops. What's their voltage? 120 volts, isn't it? That's our system voltage, 120 volts. And so our total load then, we come to find out is what?
9.5
Yeah,
amps.
9.5 amps. So it's a small load. And let's see what it says to do next. What does it say to do next in our book? We're on page 15. What does it say to do? Step 2 says check the NEC 242A for the minimum size service interest conductor. So we better go there. 240. But we ain't got much right there. 240. 42A. $230, I'm sorry, I said 240. I knew I didn't look right. The impassive service and conductor shall not be less than either 240, so we go to 1, A2, A3, will be determined. Maximum current of the bus will ace the sum of the non-continuous plus the continuous load, that's number 1. Sum of the continuous plus the continuous load after application, number 2, is what we just did. And so on and so forth, okay? So I don't see anything there that hurts us. Section 230.79, okay, that's 230.79. Rating of service disconnecting means. Service disconnecting means shall have a rating less than the calculated load, which what we've done, okay? All right, and so the service interconductors have an ampacity of not less than a load to be served, okay? And so what would our, now let's think about this. Let's go to, what would our disconnected means be then? If we've met these requirements, whatever the disconnecting means would be. It'd be 15 amps, wouldn't it? That would be our next higher common size that we'd use. 15 amps. Look there in the book, what it says. The disconnect in this case would be 15 amps. Since the total connected load for the pump is less than 10 amps, and a single branch circuit feeding the pump and the light switch will need only to be number 14. Number 14 copper, number 12 would be qualified service interest conductors, because there is no minimum. But I can tell you what I would put number 12, wouldn't y'all? Well, number 12 wire is good for what size circuit, as far as the NEC is concerned? 20 amps, isn't it? Even though a number 12 wire is actually good for how many amps?
30.
Good for 30. The code book says what? The maximum you can use a number 12 for is 20 amps, right? Okay. Let's take a break right there. Okay. Take a break right there. 5 minutes. Y'all get about 5 minutes. Y'all can sit there. Or we're gonna take 5 minutes. Because being that we're taping this and all, we kind of trying to do it per the books. So, if y'all kind of look, we actually have only one more section to get through, roadside vegetable sale. And then some example, that step we're going to get through there. So once we get through there, we'll be done. But again, we'll take about 5 minutes. Matter of fact, I'm gonna walk out to the restroom. I'll be back. Don't get in front of the camera. Not supposed to film y'all.
Yeah, he was saying something, him and Caleb were talking. I'm saying something about that they couldn't film. I don't know why, some stuff that won't be.
Well, that's more power to them, all right?
Yeah, yeah. Well, they said that they can have our voices, they just can't have us.
Probably because we ain't signed a consent form or whatever.
Yeah.
I mean, some of the stuff like at school, I proctor tests and stuff like that. And if I got an 18-year-old kid come through and they want, you know, and parent calls me up and asks me, you know, about grades or whatever, I can't tell the parents none of that because they're legal adults. Like,
Yeah.
they can't even know unless I got written permission from the 18-year-old that telling me that their parents can do it. If I
Yes.
tell them I can do it, I go to jail, I get in big trouble for it.
Yeah. Yeah, I was gonna say, cause like you said, cause they didn't sign that piece of paper stating that their parents can.
They could sue me, I guess, I don't know why. I mean, I guess some parents get a little overbearing, but whatever.
But, you know, that's like if you had any kids or anything, you know, and they say, you know, the responsible party or whoever, you know, I gotta do the same thing, or, you know, the doctors won't even see them or anything until
Yeah.
I have proof that they are mine.
Who was it? There was somebody who was, I had a buddy, I forget which one it was. But he was under 18 and he like broke his arm or something. They took him to the hospital, but they couldn't contact his parents. They wouldn't even give him ibuprofen without written permission from the parent. They had him stabilized, but he was in pain.
Golly.
Hard.
Oh, man.
Yeah, it was something dumb like that. I mean, I don't know, there's gotta be limits, that's all I'm saying.
Yeah.
The kid screaming in pain, or he wasn't screaming, I'm sure, but just sitting over there, you could tell, you know. Oh well, I wasn't there, gonna do that.
Boy, what you smirking at?
Oh, nothing, I was thinking, you can listen to the recording, it's all on there, talking about a buddy who was, broke his arm, and he was under 18 in the hospital, wouldn't give him any ibuprofen even until the parents showed up, signed a waiver saying that the hospital could help him out.
Really?
Yeah.
Camera didn't even respond. So I don't know what to think about him.
I say, cause he's missed every class. I say, cause he's missed every class.
Yeah, so far. He got a lot of catching up to do. That's for sure. Oh, let me, I'll tell you what, let me go ahead and give you your attendance sheet. You go ahead and fill them out before I forget. Let me find somewhere here.
Oh, I'm on camera. Just do me.
I would like for you to, by next class, to have done your homework, thing that I give you. If you look, we do have a lot of calculations next week, actually. Missing something here? Next week, we got a lot more to go over than we did tonight. We may talk a little bit about next week tonight, just kind of go over a few things. I think that will spend a little bit of time. Let's see how long it takes us to get this next. Thank you, James. You want- All right, 2.1.2. Roadside vegetable stand for you that want to open up your own business. One of the things I will mention there under the note talks about fault current, which may affect the size of your wire. A lot of local municipalities require now a fault current study to be done. And a lot of times that's required through an engineering department to see. Because what that does is it affects the type of gear that you put in, like the interrupting rating. And the interrupting rating for different areas or on their grid is different sizes because of that. And it really affects the pricing of the gear pretty substantially. Let's just take, for example, a typical 120 208 volt panel. A typical one's 10,000 AIC. Typical. A typical 277 480 is about 22 AIC. We do have situations commercially. I'd say about the maximum we have to do is about a 65K, 65,000 AIC, which you can tell is substantially different than 22, and so is money-wise too. And so that's why sometimes these fault current, because what you don't want to do, you don't want to put in a piece of equipment that's lower than the available fault current. You know what I'm saying? Because it could cause issues. So that is something that y'all never run into, but if you see that in the field, you may ask that question: why is this rated this and that one's rated that? And that's why, because some study's been done to determine that. Roadside vegetable stand there on page 16. We see there the picture. We're going to have a main disconnect. We're going to have a switch. We're going to have a receptacle and a couple of fluorescent lights. Another practical application, we see floor plan. We see that there. Step number 1, determine the lighting load. 2 fluorescent lights used to eliminate a 9x12. Since each contains 2 40-watt lamps, the ballast is rated 0.83 amps, which translates to approximately 100 VA. The total connected load for each fixture is 100 VA, and so for both light fixtures we get 100 plus 100, and we get a total of 200 VA for the lights. Okay. Determine the remaining loads. The only other electrical outlet in the stand consists of 2 receptacles. One furnishes a power for a refrigerator, and it's 12.2 amps. It's 12.2 amps, and it's 120 volts. So what we got to do, we got to get the volt amps on this. So we're going to multiply these two out, and what do we get? 12.2 times 120 volts.
$1,464.
Yep, that's a refrigerator. We got to add that to it. All right. The other receptacle for the other says electric cash register rated 300 and electronic calculator 200. So we get a total of that's 500 volt amps. So now we just add these 3 together, and we get what? 2,164 volt amps. Am I right there? Okay. And we're going to do, let's see, continuous load. Set number 3 then. So we've got total load so far. Step number 4 says you got to do continuous load. Continuous load in this example, continuous loads are the what? Refrigerator. Now that's probably going to run all the time, isn't it? Would hope so. Okay. And what else is going to be continuous? Probably. Yeah, the lights. So we need to add these 2 together. So that's 1664. Now what are we going to do with that 1664?
120 times it by 125.
Yeah, 1.25 is how much?
2080.
How much?
2080.
2080. What are we going to do with this 2080? This was our continuous, this was continuous. The only thing we got left is that 500 non-continuous. So now we're going to go back and we're going to add 2080 to what? 500. And so we see our actual load now is not 2164, but it's 2580. That makes sense, guys? Okay. 2580. This is a 12240 volt service though, single phase. And so we're going to take this 2580 What voltage would we divide it into it?
To 240.
240. And we come up with how many amps?
10.75.
Yeah, 10.75. And if you read there, step number 6, we check it, okay? We see there 240 for the minimum size of the service interconductor, 230.79 for the minimum rating of the service disconnecting means. Let's turn to 230.79. Not less than calculated loads be determined in accordance with Part 3. No case shall be lower than that. Okay. It actually suggests in the book that we use a number 10 copper or number 8 aluminum service interconductor in this project, which means we'd have a 30 amp disconnect. Okay, 30 amp disconnect. Because when you buy a disconnect, they're either 30, 60, 100, or 200, or 400, so on and so forth. Okay. But when you buy that disconnect, the smallest one you're going to be able to buy is 30 amp. And again, you may want to do it in aluminum. It does. It says you can do it at number 8, whereas in copper we do it at number 10. No more than it costs for number 10. I think I'd do it in copper, wouldn't y'all? And if you look there, the minimum size of the service drop conductors, NEC 230, you'd go to 230.31 for the minimum size of service lateral conductors. We're not under jurisdiction, and so you need to look at those. But I think for what we've done here, I think we're good to go in what we're trying to do. Okay. That's really the end of section number 3. We're supposed to stop right there, but it looks to me like we got a lot to cover next week. So being that we got a little bit of time, I think I'm going to go ahead and start with section 3, or section 4. Section 4. And let's just look at a few things together. Let's take some more time and look at some things here together. And then we'll call it a night. Let's at least get through most of 2.20. So, 2.20, single family dwelling. Now, it's a little bit different than we learned in the other class, but let's kind of go through the steps. It's a step process. Yeah. Floor plan, if you look at your floor plan there, you got a kitchen, bed, a couple, 3 bedrooms, a living room, and a carport. Carport you need to remember. You look there at the information it gives us. Concrete slab, no basement, unfinished attic, appliances, you got a 12 kW electric range, 4.5 kW water heater, washer, and a 5.5 dryer. In utility room, gas heaters are installed in each room with no electrical requirements. What size service entrance would be provided for this residence if no other information is specified? All right. Figure 6, which we'd turn over, is a blank form. I'm not going to look at that too much depth right now. We'll come back to that in a minute. Let's just take a look at the first 3 steps to start with. So, step number 1, compute the area of the occupancy. The general lighting load, including general receptacles, is determined by finding the area. So we got to find that. And so, how would we find what the area would be? What are we going to do to find the square foot?
Get length times width minus the carport.
Let's do this length times the width first. 48 times what?
33.
How many square foot is that?
It's 1,584.
All right. Now you hit the nail on the head a minute ago, Nate. You said carport is within this total right now, but it's not going to be a total of square foot, is it? So it's what, 12 foot by 19 and a half? How many square foot is that?
234.
What are we going to do with that 234?
Should subtract it from the 1584.
Yeah. So our grand total then is 1,350 square foot. Now step number 3, The net living area calculated 1,350 square foot. Number 4, determine the general lighting load. We're gonna go to table 220.12. 220.12, this is a residence. 220.12, general lighting loads by occupancy. And we're gonna go to dwelling and see how many VA per square foot that we're gonna do that by. $1,350 times what? How many volt amps? For a dwelling?
3.
3. So we're going through 1,350 times 3, which is how much?
4,050.
Yeah, and if you look here at your, it's that form, we see that as number 1 there. See 1,350 times 3, 4,050. But that's the first thing, if we were doing a form, we'd fill that in. Or we just, to me, if we ain't got a form, I'm writing that number down and I'm putting it off to the side. I want to remember this number right here. This is the first number I need to remember. The next step, if we turn to 210.11c, 210.11c, it says in a dwelling, what does it say about small appliances? 210.11c. What does it say about small appliances?
You gotta have 2 or more
2.
20 amp.
Yeah. 2 or more 20 amp. So, well, first of all, I don't want to forget this 4,050. I'm going to write it down. So we got 2 small appliance circuits. Those are 1,500 volt amps each. So we're going to go 2, and so our small appliance is going to be 3,000. Go with me on that? Okay. Step number 5. NEC requires at least 220 volt. If you look at step number 6, 220 volt, 20 amp small appliance branch circuit to be installed in each kitchen, dining, breakfast nook, and similar areas where toasters, and it's probably what we do. We're going to plug in a toaster. We're going to plug in a coffee maker. Would they work at the same time? Very possible. In the morning, I'm going to make it. I don't drink coffee, but if I did, I'd make a cup of coffee and I'd probably toast my toast at the same time, wouldn't y'all? Other small appliances also says 22052, so when we're right there, 22052 states a small appliance circuit to be rated at 1,500. That's where we get to 1,500. Let's turn there to check so we just didn't get that out of the clear blue air. Because really, if we think about it, I'm sure somebody wanted to ask, why 1,500? Because 22052A says small appliance circuit load. Each dwelling load shall be calculated at 1,500 volt amps for each 2-wire small appliance. Y'all see that there? That's why we did it. So that's why we got 2. The next step says there has to be a laundry circuit. 210.11c2, we go back to there. It says there has to be a laundry circuit. Let's go back to 210. C2, in addition to the number of branch circuits required by other parts of the section, at least what? 1 additional 20 amp circuit shall be provided to supply the laundry receptacle. Is the laundry receptacle the dryer receptacle? No. Completely different. So we got to have a laundry, and how many VAs is it? Volt amps is it? How much?
It's 1,500.
It's 1,500, yeah. And again, because the NEC says that's the minimum requirement for that, it's 1,500. Okay. So if we go to there, now step number 9 says to do this. Calculate the lighting load demand in the NEC 22042, note that the demand, let's go to 22042. 22042. The table there says the first, for a dwelling, the first 3,000 is what? How much percentage? 100%. And the remainder is how much?
35.
35. So we're gonna take, so let's figure out how much we got right now. We got what, 8,550. All right, it says the first 3,000 is 100%. So I'm gonna take that 3,000, I'm fixing to take it out, but I gotta count it 100%. So I'm gonna kind of plug it off to the side here. Y'all see what I'm doing? So don't forget it. And now what am I gonna do? I'm gonna take 3,000 away from that 8,550. And I'm gonna get 5,550, is that right? Yeah, 5,550. Now what am I gonna do with that 5,550 now? What does it say? It says over 3,000, from 3,000 to 120,000, we definitely don't have that much. What is our demand factor? $220.42 for dwelling. What does it say our demand factor will be for over 3,000?
35%.
How much?
35.
35%. So what do we do with that 35 then? What are we doing?
And multiply the 555 by 35.
The remainder
Yeah.
times 0.35. How much do we get?
Um, 1,942 and a half.
1,942, okay. And I think the book, yeah, we'll leave it at 42. Now what am I gonna do this 1942?
Add 3,000 to it.
Thank you. 1942, okay. I think that was the year my mom was born, 1942. 42, no, she probably wouldn't appreciate me saying that. 4,942. Okay. What we got so far, which we're in connection with the book, that's what it says. Calculate the load. Step number 10 says calculate the load for other appliances. So we're going to leave that to the side, such as a water heater, disposal, dishwasher, furnace. The water heater, what did it tell us it was in the example? Didn't it tell us what it was? Yeah, it says the water heater was 4.5 kVA, which is how much?
4,500.
Yeah, so we need to, let's just kind of put this down off to the side. Oops. Now we got a water heater. This is load. Water heater, 4,500. Just kind of put in. Let's read and see what it says to do next. 45. Calculate the load of the range. Okay. What was the load on the range? What did it say in our example? What did it say? Go back and look at it. Tell me what it said. And we started example. What did it say the range was? 12 kW? Is that what it said? Well, how do we calculate? Do we just, does that 12 kW become 12,000? No, because there's a table for ranges. 220, 55. There's 3 columns. How many ranges do we have to start with? How many do we have?
The one.
1. Okay. So we're look there. 22055 says number of appliances. Now there's 3 different columns. The first column says from up to less than 3.5. Column B says 3.5 to 8.75. The column C says not over 12. Is that the column we're in? Because there's 12, right? So we're not over 12. So what then is the kW for this one 12 kW range?
8.
It's 8. 8 kW, which is how many volt amps?
8,000.
But that's a range. Okay, that's where we're at so far. All right. So we got that so far. Clothes dryer, while we're there, let's turn to 22054. Clothes dryer. First of all, the minimum that you can have for a clothes dryer by 22054 is how many watts?
5,000.
5,000. But our clothes dryer is 5.5 kW, which is how many watts?
5,500.
5,500. And so how much is our value for our clothes dryer going to be?
5,500.
5,500. All right, clothes dryer. But it says now, if we had 4 more, we could reduce, couldn't we? If we had 4 more appliances, we don't see that anywhere. That's what the note says. All right. Calculate the larger of the heat or air. It says what? What does it say about that? It says it was what? Gas in each room? But there really was no. In fact, if you look at the note, it says if gas air is used, the blower motor will have been included in step 6. If some form of electric heat is used, this load would be compared to the air conditioning. But it didn't say anything about that. Okay? So we don't have none of that in this example, do we? By what the example it said, we don't have heat and air, do we? They must live up north. They must not need air conditioning. So now we're just going to total the loads. 4942, 8,000, 5,500, 4,500. And how much are we going to get?
Should be 22,942.5.
Yeah. And what are we going to do? That's watts, right? Now what do we need to do with that watts to get amps? Because to figure our wire size, we got to get the amps, don't we?
Divide by 240.
And that's equals to what?
96 amps. Roughly.
96 amps, roughly. I agree with you. Okay. Now we're going to go to required cert. We're going to go to, we would see that the minimum required service would be, determine the service. Let's go to 23042. See what it says. And it just talks about the minimum size and ratings, which we've done all that. Okay. If you read there in the book, it says that the typical, you know, is a 12240. We're not going, you know, our typical would be, if you look there below, it could be that this would be a minimum size service of what? If we got 90, what are we going to do with the minimum size service? We're going to do 100 amps, aren't we? 100 amps. Okay. But what did it ask us? Okay. Is that all it asked us? I think that's all it asked us. How about wire size? Just while we're there. Okay. Well, I think it may actually do that in the next thing. No, it doesn't. Let's just go to wire size. What would our wire size be? Let's go to 310, 15B16. Well, let's determine, are we going to use 60 degree or 75 degree column? Let's go to 110 to start with and determine that. Let's go to 110, 14C, 1 and 2. 110, 14C, 1 and 2. The termination provisions of equipment for circuits 100 amp or less shall use conductors rated at what degrees? 60 degrees. Is this 100 amp or less? Yeah. So now when we go to 310, 15B16, we're going to use which column? We're using copper. The first one. 60 degrees column. Well, and we're going to find out what size of wire would be used for this service. Copper.
Should be number 1.
Number 1. What size aluminum would we use for this service? If we want to do aluminum, being it as a house?
Why not?
One off. Okay, one off. Any questions so far tonight? Everybody understand what we're doing? Everybody understand what we just did? We're gonna stop right there. Stop right there. Okay. All right. Y'all have a good evening. Do the homework between now, we'll go over that first. When we get in here next week, we'll do that first. And then we'll just kind of go from there, guys. Okay? All right?
Tell you what, Alabama's looking good after the first two games.
Yeah?
I was kind of worried about them there the first two games. They didn't show up.
Yeah.
Not too good. And then after that, I was like, yeah, there they go.
Yeah, they kind of, like they got a little something to prove right now. Something, I think.
Yeah.
So, still think it's gonna come down to them and Clemson probably. So,
Yeah, that's why I figured the way Clemson's playing again this year, it's gonna be Alabama.
It looks